All right, so one of the things that scientists use momentum for is to inventory and analyze collisions. Okay, and one of the reasons we use momentum for that is because in certain conditions it can be conserved. The momentum can be conserved. So we break we break the collisions into two types. Okay, the first type is called an elastic collision, and the way the collisions are categorized is to whether or not kinetic energy is conserved. So if two things collide and you find the kinetic energy is conserved, then that collision is said to be an elastic collision. All right, and I'll show you a video of that. So an example would be, let's say I have two billiard balls on a table. Okay, and I'm going to show a video of two cars. Okay, they're going to collide, all right, and they won't stick together because I'm going to use magnets so they never actually touch. But I'm going to use an example. Let's say two billiard balls, right? They're made of glass. We're going to ignore the rotation. We'll ignore the friction on the table, all right? So here I have, again, and I'm not drawing the table, okay? So just simplify this. I have two billiard balls, and I'm going to use them to simplify this, say they have the same mass. Okay, that's number one. That's number two, the same mass. Here's my before picture. So in the momentum problems, you need to have two diagrams. You need a before diagram, you need an after diagram. So in the before picture, I have this one coming in, initial velocity v0. This one's at rest. Okay. In the after picture, okay, well, in the collision, number one hits number two. And the after picture, number one stops, and number two goes out with the same speed that number one had. Okay, now we're not proving that. Okay, we'll prove that second part of the chapter with a bunch of algebra, but the video I'll demonstrate that. Okay, maybe you've seen it playing pool or playing air hockey. This one comes in. If it has the same mass as this one, they collide. First one stops, second one goes out with the same speed the first one has. Okay, so let's see how this one turns out to be an elastic collision. Okay, so initial momentum is mv0 because only this one's moving. That one's not moving, so it's momentum 0. In the final picture, remember these have the same mass, and doing special case at the same mass. And we said this one goes out with the same speed, so P final is equal to P initial. Oops, I'm missing a little arrow right there. Okay. All right, so again, I haven't proven that. Okay, we can prove it algebraically, and we'll see that in the video. Okay, initial kinetic energy is just for number one. So 1/2 mv0 squared. Initial kinetic energy, this one's 0. Okay, it's not moving. Okay, in the after picture, final kinetic energy of this one is 0. Okay, that's 0. And then final kinetic energy, the other one that's moving is number 2. K final for this one is just 1/2 mv0 squared. So in this collision, initial kinetic energy is equal to final kinetic energy. So that would be an elastic collision, and I'll show you that in the video. Okay, now, so that was an elastic collision. And in the lab I'll show you this week, we're going to represent an elastic collision by putting like rubber band bumpers on the cars. So where kinetic energy is conserved almost about like 98%. Okay? So ideally, anytime you would have contact, you would have friction. So an elastic collision would be an ideal case. You can design a collision where very little energy is lost, okay? But an elastic collision would be an ideal case. So anytime two things interact, okay, there's always some friction involved. The other type of collision, okay, remember, the two types, they're categorized in terms of whether kinetic energy is or isn't conserved. The other type of collision is an inelastic collision. And a collision is said to be inelastic if the kinetic energy is not conserved. Okay. Now, why is the kinetic energy not conserved? So in an inelastic collision, the objects can bend or deform to lose kinetic energy. All right. And an example of that would be, I'll show you a video of a baseball colliding with a bat, okay, golf ball colliding with a club, and you can actually see the objects deform.
Call to another lab.
This is the only place in the country where you certify the bats and the baseballs in the major leagues.
Welcome to the University of Massachusetts Lowell Baseball Research Center.
Okay.
At 10,000 frames per second, we can see that regulation hardballs turn into squash balls when they hit the bat.
And right here, you can see the ball is actually starting to wrinkle.
Right, it has to go somewhere. That, to me, looks like a fake baseball.
Yeah, that's a real Major League Baseball.
If I just saw a frozen frame of that, I would think that you really destroyed this ball. This is about a third of the ball compressing almost flat. That would take, 50 or 60 of me standing on top of one of these to make it compress like that.
Or a couple cars.
Or, we hasten to add, a professional ball player. So the ball's not even as tough as we thought. But that just makes the sight of a splintered bat all the more mysterious. What gives? Clearly the ball, but what else?
So in this shot, we see the full bat.
And the bat bends too?
This makes me feel like every single piece of equipment in baseball is made out of rubber.
My name is Paul Furs, and I'm the head of Test Methods Development at Titleist. We can take measurements of the ball, and we know precisely what the time is from one frame to another. So we look at it as a series of still pictures, and we can look at the mechanics of how the ball impacts the club and how that translates into spin and speed and launch angle.
All right, so why is kinetic energy lost in the collision? All right, so when the objects deform, all right, there's heat generated. Now, let's say if you took a rubber band, find a rubber band on your desk, okay, put it up to your lip, okay, the rubber band feels cool, it's at room temperature. Now take the rubber band and stretch it really fast and put it up to your lip, okay. The rubber band feels really hot. Matter of fact, if you keep stretching the rubber band a bunch of times, okay, eventually it gets so warm that the rubber band breaks, all right. So now imagine you take a ball, maybe a tennis ball or something softer like a foam sponge ball, okay, and you wrap the rubber band around it, that's the rubber band, okay, and you bounce the ball off the ground, okay, so every time the ball hits the ground, it deforms a little bit, okay, or take your finger, that's a finger, that's another finger, and keep squishing the ball in rubber band. So every time you squish the ball, it's as if it deforms and hits the floor. So not only is the ball deforming, but you have the rubber band attached to the ball, it's deforming. So when you deform the rubber band and put up to your lips and got warm, okay, that's just like when the ball deforms when it hits the floor, or when the ball hit the bat, or when the golf ball hit the club. Anytime you have that deformation, you're generating heat. Okay. Another experiment you could do, you could take a foam ball about the size of a tennis ball, okay, something you can squish really easily, okay, kind of something spongy, a soft foam, okay. Take the ball, stick a meat thermometer in it, kitchen thermometer, okay, and look at the temperature. It'll measure room temperature, all right. And then take the ball in your hand and sit there and squish it for about 10 or 15 minutes, and then stick the thermometer in. You're going to see the ball gets warmer. Okay, so all that deformation generates heat. So when the ball collides with the bat, okay, when it collides with the floor, or when two things collide and they deform, the kinetic energy due to motion gets converted into heat. So that's why every time you have objects collide, okay, they bend. Okay, now they could deform like the metal of the car permanently deforming, okay, and you lose kinetic energy. So that's an inelastic collision, right? Now, one type of inelastic collision is if they stick together. Okay, and if they stick together, some books call it completely inelastic, or some books call it perfectly inelastic. So for completely inelastic or perfectly inelastic, the objects stick together. So, and we'll see a video of that. So an example would be I have, let's say, two objects. I have two pieces of clay or mud. Okay, they're moving at each other. This is M1, this is M2. I'm making the masses equal. Okay, so they're going to be moving at each other. Okay, not at the same velocity, because one velocity is positive, one's negative, but they're moving at each other at the same speed. Okay, so I'm going to do a special case just to show that this is what you would expect, and I'll show you a video on this. So two objects coming at each other, same mass, same speed. Initial momentum, okay, is mv0 for the left one minus mv0 for the right one, because this one's headed to the left, that one's headed to the right, so that one's negative. Okay, so initial momentum 0, they add to 0. So maybe this momentum is 3, this momentum is minus 3, so they add to 0. Okay, all right. Initial kinetic energy, remember kinetic energy is a scalar, 1/2 mv0 squared, 1/2 mv0 squared. Okay, those are positive. So initial kinetic energy is that. In the after picture, we're going to see in the video that they when they hit, they come together, stick, and they stop. Okay, and the reason they stopped is because they have the same mass and the same speed. All right, so they stop. So final velocity is 0. So over here, initial momentum 0, final velocity is still 0 because they're not moving. I mean, initial momentum is 0, final momentum is 0 because they're not moving. Okay, final kinetic energy. Okay, remember kinetic energy is 1/2 mv squared. Final kinetic energy is 0 because they're stopped. So here, okay, 100% of the kinetic energy is lost. Okay, so here, before picture they're moving, final picture it's not moving. So all the kinetic energy is dissipated in the form of heat. So the I'll also show you a video where one car comes in. Okay, it collides with another car that's not moving, and then they both move off at one common speed, stuck together. Okay, so that's an inelastic collision, right? It's completely inelastic because they stick together, and in that case, kinetic energy is still lost because when they collided and stuck together, you still had some kinetic energy being dissipated by a friction force. So in actuality, anytime you have a collision, you always have some type of friction in that collision. But if we wanted to make an elastic collision, we can almost we can almost mitigate the kinetic energy loss if we use magnets, okay, or if we use little rubber band bumpers. And that pretty much simulates an elastic collision. But I will show you a video of the inelastic collision where they stick together and stop, and where they collide and then keep on moving.